Hi colleagues, welcome to the Digger Science channel. This time, we will learn to calculate the moment of inertia of a rigid body using Riemann sums. The rigid object is a thin stick. A thin stick is lying in the xy plane, rotating about an axis on the z-axis, where one end of the stick is the axis. Before going any further, let's get acquainted with the concept of Riemann sums briefly. In Riemann sums, we will divide the rod into several elements in equal intervals of length and units. This element is also known as an increment. So, the element in calculating the moment of inertia is a mass element. We can think of them as very small particles. Based on the discrete particle concept, the moment of inertia value is the sum of the moments of inertia of each mass element. That value can be written as I of n discrete object units is sigma mi or I squared. The true value of the moment of inertia will be known when the value of n goes to infinity. Or I is lim of in when n goes to infinity. Back to calculating the moment of inertia of the stick. Let's assume the length of the stick is L. We will divide the stick into infinitesimal mass elements, the number of which is n. The width of each mass element is the same, namely L over n. Thus, the partition point in the coordinate plane is 0. L over n. 2L over n. 3L over n. 4L over n, and so on until it reaches L. If the mass of the stick is big M, then the mass of each mass element is big M over n. This is because uniform objects will have the same density. So mass elements with the same length will have the same mass. The distance of the first mass element to the shaft is 0. So the moment of inertia of the first mass element is big M over n, times 0 squared. In the same way, the moment of inertia of the second mass element is big M over n, multiplied by the square of L over n. The moment of inertia of the third mass element is big M over n, multiplied by the square of 2L over n. The moment of inertia of the fourth mass element is big M over n, multiplied by the square of 3L over n. And so on, until the moment of inertia of the last mass element is big M over n, multiplied by the square of n minus 1L over n. To simplify calculations, exclude the big M over n factor. Apart from that, we will also exclude the square of L over n factor. The values in brackets indicate regularity as a series. It can be written as sigma of I minus 1 squared. Now, decompose the value of I minus 1 squared into I squared, minus 2I, plus 1. Using the properties of sigma notation you will get sigma I squared, minus 2 sigma I, plus sigma 1. Based on the previous tutorial, sigma I squared is equal to 1/6 of n, times n plus 1, times 2n plus 1. Sigma I is equal to half n, times n plus 1. And sigma 1 is equal to n. Simplifying the values in brackets we get 1/3 n to the third power, minus 1/2 n squared, plus 1/6 n. So, the approximate value of the moment of inertia is In equals big ML squared, times 1/3, minus 1 over 2n, plus 1 over 6n squared. Well, the actual value of the moment of inertia is obtained when n goes to infinity. Well, the factor of 1 over n, and 1 over n squared will go to 0. So, what we're left with is I equals 1/3 of big ML squared. This is the moment of inertia of a stick rotating horizontally at one end, I equals 1/3 of big ml squared. To summarize, in the Riemann sum method, a rigid body can be considered as a collection of discrete particles. Hopefully this tutorial can provide useful benefits. And don't forget to watch the next video.